This is the inverses of functions, and I have a theorem for you. This is 12.1c. We've got two previous videos that are linked in the description. All functions have inverses, but the inverse is not necessarily a function. Look at this example. We've got m equals this set of four ordered pairs, and the inverse of m would be the x and y values interchanged. Well, this is not a function because the ordered pairs 3 and 1 and 3 and 6 have the same first coordinates of 3, but different second coordinates. And a relation that's not a function may have an inverse that is a function. If the inverse of a function f is also a function, we read and write it as f inverse, and f with a little -1 exponent, or f with the little -1 exponent with the x in parentheses. And remember that we get the inverse of a relation by interchanging the x and y coordinates of each ordered pair. We learned that in the last couple of videos. So the domain of a function f is the range of f inverse, and the range of f is the domain of f inverse. And also a function can be its own inverse. The function of x can equal an x, or the inverse of x, or the quotient of 1 and x. When a function is defined by an equation, sometimes we can find an equation for its inverse by interchanging x and y. When we're given f of x equals 3x plus 1 and find an equation for f inverse of x, we can think of the given as y equals 3x plus 1. Just put a y there instead of the f of x. And we interchange that x and y and get x equals 3y plus 1. Well, now we solve for y. We add a -1 to each side and then divide by the coefficient 3 and get y equals the quotient of x minus 1 and 3. So f inverse of x equals the quotient of x minus 1 and 3. What's happening is f assigns 3x plus 1 to any number x. It multiplies each number of the domain by 3 and adds a 1. And its inverse, f inverse of x, assigns the quotient of x minus 1 and 3 to any number x. So the inverse function subtracts from each member of its domain and divides by 3. So it was adding 1 and multiplying by 3. This is subtracting 1 and dividing by 3. So the function and its inverse are inverse operations. We're going to let s of x equal the square of x and find an equation for s inverse of x. Think of it as y equals the square of x. And notice that the domain and range of both consist only of non-negative real numbers. So we're going to interchange the x and y and get x equals y squared. Now we're going to solve for y squaring both sides. We get y equals x squared. So s inverse of x equals x squared, as long as x is not negative. And the function s assigns that square root of x to any non-negative number x. And the function also takes the square root of any input. And its inverse, s inverse, assigns x squared to any non-negative number x. So the function squares each input. So the function and its inverse use inverse operations. If f of x equals 2x plus 3, then f inverse of x can be thought of as the inverse of y equals 2x plus 3. When we swap places, we interchange the x and y and get x equals 2y plus 3. We add a -3 to each side of the equation to isolate the y to solve for y, and we divide by the coefficient 2, and we get y equals the quotient of x minus 3 and 2. So that means f inverse of x equals the quotient of x minus 3 and 2. We can substitute real numbers to prove the two functions are inverses. If we put a 5 here, we've got the function of 5 equals 2 times 5 plus 3. Well, that's 10 plus 3, that's 13. Then the function inverse of 13 would be the quotient of 13 minus 3 and 2. That's 10 divided by 2. That's a 5. It worked. And this shows that if we find f of x for some x, and then find f inverse for the number, we'll be back at x again. And in function notation, the statement is f inverse of f of x equals x. F inverse of f of x equals x. So just think of the parentheses as the of, okay? And it means that we work from the inside out to take x, then find function of x, the f of x, and then find f inverse for that number. Then we'll be back where we started at x. Now, for similar reasons, this is true. The function of f inverse of x equals x. So for these two to be true, x must be in the domain of the function that is being considered. So that brings us to our theorem. It's a helpful theorem. For any function f whose inverse is a function, f inverse of f of a equals a for any a in the domain of f. And also, f of f inverse of a equals a in the domain of f inverse. So check this out. For the function f of x equals 4x plus 9, we can find f inverse of f of 283, and we can find f of f inverse of negative 12,045. We see that every real number is in the domain of both f and f inverse, so using our theorem here, we can immediately write our answers without calculating. No calculation involved. Whatever's in the parentheses, that's the answer. F inverse of f of 283 is 283. And this one is negative 12,045. See? Does that make our life easy? Okay? So, to be sure that two functions are inverses, we have to do them in both directions and show that both result in the single value x. It brings us back to where we were. And our next video is 12.2a, and we're going to talk about exponential functions. I'm going to have a link to those two previous videos for this chapter that are very helpful, and a link to the Algebra II playlist, which I'm going to add this to, all in this description, along with the links to YouTube fan funding and Patreon, and now I've added PayPal. So if you'd like to support what I'm doing and help me out, I'd really appreciate it. I'm trying to make my videos all free and available to everyone around the world so that they can get math help, and if I've helped you, I'd really, really appreciate the help back. All right? I hope you're doing well, and I'll see you next video. Bye.